Okay, I welcome today to our online training for students. I'm very happy that we can do this today for you because in our opinion, you are the future engineers and therefore it was the decision from Dlubal to invest in the future. And I'm very happy to moderate and also be the moderator of today's online training. So today, part 4 of our Rfem 6 series for students. Today we do the introduction to steel design. Few words about me. My name is Daniel. I am responsible here at Dlubal for our human resources and also acting as Chief Operating Officer for the most important managing decisions. Next to that, I am also responsible for the marketing and sales here at Dlubal. Today with me, Markus, who will support me with the chat by answering your questions. Markus, would you like to introduce you?
Hello, my name is Markus Baumgartel. I am responsible for customer support and frequently asked questions on our website. And today I will help my colleague Daniel to answer your questions during this introduction. Thanks.
Thank you, Markus. So I will disable my webcam, then you can see more of your screen. So I will lose a few words about that technical platform GoToWebinar. So for those who are visiting or attending the webinar for the first time, you can show or hide your control panel here, adjust your audio settings. So for those who can hear us, check please your loudspeakers and please ask questions. If you have any questions, Markus will answer you these questions as good as possible. So regarding the last training about the introduction to FEM or finite element analysis, which was last week, you will get these materials and also the recording and certificate this week. So don't worry, you will get these materials, and also this session will be recorded and will be published on YouTube, and you will also get the recording of this training. So today we will handle the steel design. So what gonna we do today? So first of all, I will give you a theoretical background. Don't worry, it won't be a kind of class lesson like in your study, just the most important things in a very short time. Then together we will model a kind of two-span girder. So it's kind of introductory example where we do kind of modeling and then apply loads, do the calculation, and then the design of this steel beam. Then I will give you some few information about imperfections and also stability proofs or stability design checks in the ultimate limit state. And in the end, we will model a flat hole frame where we go also deeper to the applying of imperfections and also the stability design check. Okay, perfect. So I have prepared also some polls in order to create this session more interactive. So right now, in order to evaluate your experiences with the Eurocode 3, this will be a kind of Eurocode 3 training. Please answer me these questions if you have already some experiences with Eurocode 3 and our software. Okay, let's take a look to the results. So yeah, most of you have chosen that it's very new and or you have not so much experience. So today this training is perfect for those guys who want to get a rough overview and rough insight into the design of steel structures in Rfem 6. Perfect. Okay, so what I choose the right one. So now, okay, so what do we have for products for design according to Eurocode 3? So we have the basic add-on steel design, and the big advantage here is that you have all international standards included. So when you would like to perform your steel design according the Eurocode, then you can do this, or the American standards, also possible, or kind of Swiss standards, also possible. So this is the add-on we will cover today. You have already learned some other add-ons like our section, our structure stability, and also the nonlinear material behavior. On top of that, we have also another add-on like torsional warping. The warping torsion add-on considers 7 degrees of freedom and allows you to consider cross-section warping as an additional degree of freedom when calculating members in Rfem or in SRSTEP. So stability problems such as torsional buckling and lateral torsional buckling can be considered by giving you these eigenvalues and also these buckling shapes. On top of that, we have also the add-on steel joints. Now you can design all possible steel joints based on a finite element method, and this makes you very flexible in designing and modeling different types of joints or steel connections. Okay, so safety concepts in steel design, especially in the Eurocode. So what do we have here? Generally, we put the design effects and compare them to the design resistance, and the design resistance is composed of the characteristic resistance divided by the safety factor. And here we have this according the Eurocode 3 1.0. When we are in Germany, we have also the national annex in the standard, and there we have, for example, the factor of safety. This is gamma M1, and here we have a stability analysis factor of 1.1. So when you are in Germany, you have to consider the differences between the normal standard and also the national annex. So when the design effect is below the resistance, then the design check is fulfilled. Okay, then the next thing, elastic or plastic global analysis. This depends on the cross-section class you have. So in general, we have 4 different cross-section classifications, so 1 up to 4, and the cross-section class 1 has one interesting characteristic. It has a high rotation capacity, and this allows us also to perform the design, the cross-section design, with a plastic global analysis, and also we can consider here the cross-section resistance as plastic. So cross-section 1 reaches a high plastic moment resistance, you see it here in the diagram, and also a high rotation capacity. And this is also the reason why a plastic hinge can develop well and can be applied, but not anymore for the cross-section class 2. So this is interesting to know. And in general, you are always on the safe side when you perform the cross-section design checks with the elastic method. So you take into account the elastic global analysis, which is pretty normal when you calculate with Rfem, and also take the elastic resistant cross-section values. So much to the elastic or plastic global analysis. So now let's do the first example together. We have here a 2-span beam. We will model this and run a normal cross-section design check over this 2-span beam. Important there that we want to check the cross-section classification and also perform the cross-section design checks no stability design check is considered there. This will be part of another example. And then I will give you an introduction to the difference between elastic and plastic cross-section resistance, and show you also how to activate the elastic method and also elastic plastic method. Okay, so let's jump right into it. I will open Rfem 6 and create a new model. So for those who would like to model with me, now it's the right moment to do that. I click here on File, click here on New, and enter here a name, two-span beam. I refer to my two-dimensional plane view, so this one, exact and plane stress. And now it's important to activate the add-on steel design. So every time when I want to design different materials, I have to activate the design add-ons. I activate this, and now I have to jump to the next register, standards, and here I have to choose the standards for which I would like to consider my design. So standard group Eurocode, because we are here today very international. I leave this setting like here. So I refer to the general Eurocode, also the standard group for the load wizards, and also the national annex for the steel design. Yesterday I did it with the German audience, and that we have chosen the German national annex, but for this day it's okay when we choose the European. Okay, I click on OK. So, and now I refer to my view in the opposite of the global Y direction, and I create my first cross-section. So for this simple example, we create one cross-section. This will be an IPE 550 profile. So I go here to the symbol bar, click here on New Single Member, and choose here a section. I have already created this section IPE 550, but for those who would like to model with me for the first time, no problem, I will create it again. I click here on Create New Section. And the biggest advantage now here in Rfem 6 is that we can search for a cross-section or profile. So I enter here IPE 550, and now I can choose from the list here, and I choose this one, Euronorm, and I choose here this material S235. It's the same. So to create this one, it's the same behavior like for the creation of new sections. But I will also take here a deeper look, because when I activate the add-on steel design, a new tab appears here in the materials, and I see here, for example, these safety factors or these partial factors for materials. And this was one of the PowerPoint slides where I have shown it to you. So here we have these different gamma M values, gamma M, M1 for stability failure and so on. And when you would consider the German national annex, you would have here a value of 1.1. But because we do this European one, we have here only 1. So interesting to know, because with these values and with these partial factors, the Rfem 6 is going to perform the steel design. Okay, I cancel this. I click here IPE 550 and I click on OK. So now I draw the beam, and the overall length of this beam is 24 meters. Because I don't know where here's the grid point of 24 meters, I can make it quite easy. Just go through and snap grid point and enter here a value of 24 meters, and right click, cancel this command. And now the next thing is that I divide this beam here in the middle. So right click, member, and divide member exactly in the middle. I don't want to create two separate beams or members, so I have to activate this option here. I click on OK, and now I see here this node, and this node is part of this beam. Double click on that, and I can see here this node type on member. This makes it quite easy for load application, but also for result interpretation, but also for the boundary conditions, applying boundary conditions for my steel design. Okay, so this was everything. Now I have to apply support. So I click here on nodal support in the symbol bar and create a new nodal support, because I have to activate also the rotation around the global x-axis, because I want to prevent I want to prevent the own rotation about his own longitudinal axis of this beam. So I have to activate this. It looks like that. I click on OK. I choose this node here. I click on OK, click apply, and now I choose on the roller support in the global X direction, and I choose the other nodes in order to create this, and I click on OK. So now I want to display them a little bit larger. So right click on them and change the size of the graphic. Okay, the next thing is the loading. So for that, I go here to the load cases, go here to the load cases and create another load case with imposed load. And the action category is this one, so storage areas. Because when I combine these load cases into one load combination, depending on different combinatorics, combinatorics, then these action categories are important. Okay, so self-weight, imposed load, I think this is clear. So I choose here load case 1, then it jumps to this load case and I apply the loads. We have distributed member loads. So I'll go here again to the symbol bar and insert here a value of 8 kilonewton per meter. Choose this member, and this is now the advantage of this node, which is part of this beam. I say apply it next. Now I change the load case here, change also the load magnitude, and choose this beam here. I click on OK, again on OK, and now we have here these two load cases. Perfect. And when I take a closer look to the load combinations, I see here these two and in order to neglect the other one, so the serviceability states, I can deselect or I can delete them. Just go here to the design situations. The design situation gives you an overview about the situation of the ultimate limit state and also the serviceability state. For me right now, only the ultimate limit state is interesting, so I delete the other ones, and I can also do a short information about the combination rules. And here you can see, okay, how the permanent actions are combined with different partial factors and also the different the variable actions and so on. This is pretty important when you have several load cases with different action categories. Then this information about combination rules is pretty important. Okay, good. Generally, the load combinations are calculated according to the second order or P delta. So I make the force equilibrium to the deformed system. And this is pretty important. We have already learned this in the first, also in the first session of our online training series. So remember that. So here, these two load combinations, also with different partial factors or safety factors, 1.35 and 1.50. Okay, I say okay. And now I can calculate it. So I click here on calculate all. And you see here, okay, how these load cases and also the load combinations are calculated, depending also on the power of my processor, so on my CPU. And the more powerful your CPU is, the faster the calculation is done in Rfem. Okay, so I think the static analysis is pretty clear. So here you can check the different internal forces, yeah, and normal forces, and also shear forces. But yeah, this is nothing new for you. For me, it's more important to see the design for steel structures. So on the left side in the navigator results, I have here a second option, depending on the activated add-ons, steel design. And the same information about results I have also here in the tables. So first of all, here in the graphics, I see these kind of things. So the ratio envelope, pretty interesting. And also in the table below at the bottom, I see a kind of overview. Okay, so what can I see here in the overview? At first, a kind of warning or arrow, because no effective lengths or boundary conditions are designed for my stability design. But this doesn't matter. Nevertheless, Rfem considered the design of steel cross sections. So he did some steel design code checks. So let's go here to design ratio on members. And here we can see he made design check for the section proof, shear, and bending about y-axis. In this case, this is the design ratio by the design situation, but I can also take a look and choose here the design ratio by members and also by the location. Then you see here at every location where he did the design. So much to that. And now let's come to the, I would say, to the best thing here in Rfem 6, the output of this design formula. Because when you are a student and you calculate the same thing right here now, you would like to compare your results with I would say with a structural analysis program like Rfem 6, and you don't know how to see if the results are correct, but Rfem 6 offers you the possibility to see exact the way of performing such a steel design. So double click of one of these proofs, or activate here the design check details in the symbol bar of the tables. Click on this bar of the symbol, and what you can see is here the perfect described and explained design check according to the Eurocode. On top of that, also the reference to the line or an equation of the Eurocode, and now you can compare it to your calculated results. And when I was student, I missed that so much in other programs, and now we have finally it in Rfem 6, and it's so a huge advantage for you students in order to calculate your hand calculations and then compare your results with Rfem 6. So let's check what we have here. I will go through this thing here. So at first we have here the material properties based on the material we have chosen for the design. I think, yeah, pretty clear. on top of that, also the whole section properties in order to calculate the stiffness. And next to that, also the design internal forces. So with which internal forces we go to the steel design. And now we have here the design check, in this case, the shear and Z-axis. So we have here the design shear force resistance with 980 kilonewton. And also then the design component for the shear force and so on. And also here the design check ratio. This is pretty interesting. Now I can also change to the bending about the Y-axis. It looks like that. So we see here the design bending moment, the yield strength, and so on. And this makes it very attractive for you students, because the program is no black box. You see what was done in the program, and this will give you always a very good overview about the proof of this steel structure. So now let's go to the section classification. We have an IPE profile 550, and normally these cross-section classes are considered automatically in Rfem 6. So we have here different subpanels. I will come to that later on, where we find these subpanels, and here he performs the different the cross section classification. And we see here, okay, for that design, according to our internal forces, we have here this class 1. So it's very important to consider this C to T ratio. So in this case, we have here this 42. We have here these different CT limits for class 1, 2, 3. And when this CT ratio is under or between these limits, then these cross-section class is determined automatically. In this case, it's below this 72, so we have class 1. Okay, and we see here, okay, this is both sides, so this is the flank of this structure. Okay, now how can I see these different subpanels? We have every time the information about the whole section or cross-section. Go here to the section information, and now you can see the section values, the stress points, where it performs the, I would say the elastic stress design, and also here the sub panels. And now here we can see, okay, we have here this this flank and also this web here, and so on. And when I click on one of this, I see, okay, this one is both sides and this one only one side. And this is the reason why it considers here also for this sub panels. Okay, and let's close this and take a closer look to the section proof, how it was performed. So here we see plastic design. And when you take when you refer it to one of my first PowerPoint slides, I will show it to you here. So this one, then it is allowed that we take into account the plastic cross-section resistance. This is something we can consider when the cross-section is or has the cross-section class 1 or 2. So whenever you have the possibility to do this, then consider these different cross-section resistance. So plastic when you have cross-section classes 1 or 2. When you perform when you would like to perform your elastic design, so with elastic cross-section resistance for bending moment, for example, or shear resistance, then you can also change this. So again, I go here to the bending moment, and here you can see, okay, the design moment resistance M plastic, you see here, okay, 655, because we can't perform the plastic design. And Rfem normally calculates or considers these cross-section classes automatically. Where I can see, where can I see this? When I go here to the input data and go here to the sections, here I find the section classification, and for this IPE 550 profile, it is automatically determined. But I can also choose here different classes. So normally in the study, I perform some basic elastic stress designs. So now I want this also to consider here in Rfem. So now I have here several possibilities. I would like to show you one possibility. On the left side of the data navigator, you find, when activating the add-on steel design, 2 additional objects, or two additional folders, I would say. Okay, so we have on the left side types for the steel design. This will be important when we perform our another example, effective lengths, boundary conditions, and so on. And then we have also the steel design, where we can do several options. So, and here also the ultimate configurations. So, and now it becomes important, because now we want to change the default situation, the default settings. So right click on that, edit, and here you find several information about the design parameters, also an additional tab for the stability. When this is checked in order to perform stability design, the standard is that it's normally checked. On top of that, we can also activate the elastic design also for class 1 and class 2 sections. So I activate this, and this ultimate configuration is part of the beam of this member. So when I go here to members, you see, okay, here we have the ultimate configuration default, and this ultimate configuration refers to the members. Okay, now let's do the steel design again. And now you see also here we have another value, another result for the ratio. I go here again to the design ratio on members, and now you see here, okay, the section proof was done, but with an elastic design. Let's go to the elastic design. And here we see the design check ratio, okay, but now we have here not the plastic design with the plastic moment resistance. Now we have here a normal stress, or an elastic stress design with the ratio of the axial strength and the axial stress. So, and this is the difference. Okay, and now you can also see the stresses on the section. So let's go here to diagram and section. And now you can see here the diagram of design ratio, but also the stresses. So here we have the sigma x, so the normal stress due to bending moment about the local y-axis, but I can show me also the shear forces. So pretty interesting. And in order to see maybe the different points where this design was performed, I can also activate me here the different CT parts for the cross-section classification, but also here the stress points. Here you see the stress points. And the stress points you can also activate here. Oh, sorry. Yeah, so much to that. Okay, good. this was a very easy, I would say, cross-section design check, and I have prepared one more post in order to summarize now this chapter. Okay, most of you have chosen. Now let's share the results. And yes, the most of you have chosen the right answer. So when I want to perform a plastic structure analysis, then it's only possible when I have cross sections with the class 1. Okay, good. The next one is this one. Okay, let's close this, show you the results. And yes, so when I want to do an elastic calculation method, then it's possible for every cross-section class. And therefore you can use it every time. Even when you have cross-section class 1, you can use this. It's on the safe side, definitely, but economically you are quite conservative, and you could get better results when considering also the plastic resistances. Okay, so let's go ahead with the PowerPoint. So we have here now different effects of deformed geometry of the structure. So I explain you what I mean by that. So in the first online training, we have learned the difference between the calculation of geometrical linear analysis and the effects of second order analysis. So, and this makes a very important role in the whole topic of imperfections. So let's take a look. When I perform here a geometrical linear analysis, it makes no difference if I have here a slender column or really thick column. The results are, according to a first order analysis, the same. But when I perform a second order analysis and I have here a very thin column and on the right side a very large column, then it makes a difference, because the slender column receives significantly more bending moment at the base point, since the head deformation is also much more. Therefore, the proportion of additional moments due to the compressive force is larger. And this is something you have to consider. For thick profiles, it makes no huge difference, but for very slender columns, it makes a huge difference, and this is normal in the design of steel structures. So, and then we have also the critical load factors. So when you have a critical load factor bigger than 10, you don't need to consider second order analysis effects. But when it's between 1 and 10, you have to consider it in order to consider these effects. And then you have to calculate according to the second order analysis. And this is pretty important to know, and you have to know this. And and the critical load factor is the ratio between the critical load and the existing load affecting this building or affecting this structural component. Okay, why I tell you this? Because this has always something to do with imperfections. So in general, what are imperfections? Imperfections are manufacturing related deviations in the model geometry and in the material properties. So what could it be, for example, real misalignments or tolerances in the production? So when I manufacture some steel profiles, when do I hot roll it, so of rolled sections, and there it can be possible that some internal stresses appears, and these kind of affections need to be considered, because what we do the whole time in the structural analysis programs is to consider ideal models, but the reality is not ideal. So in order to consider these effects, we have to apply imperfections. And now we have different kind of imperfections. We have on the one side kind of geometric imperfection, like this initial sway imperfection, and also structural imperfections. And both are taken into account as equivalent geometric imperfections. So we summarize these two different into one geometric imperfections. So on the left side, we have here this initial sway imperfections. So this is applied on the structure and considers an inclination of our whole structure. So it's a kind of global imperfection, and there we consider a default value with 1/200. When I have here additional effects like the height and also the rows of columns, I can make it smaller, this value. Then on the right side, I have here this initial bow imperfection. This is a kind of pre-curvature, and this is a local equivalent imperfection applied to the members, and depending on the respective profile, the yield strength, the buckling curves, and also the analysis method. So, and both of them can be summarized and applied on the structure as equivalent horizontal forces. So this is one thing. How can I consider imperfections too? Is with buckling shapes or buckling forms. So I do a kind of buckling calculation or buckling analysis with our add-on stability or structural stability. And when I see here this buckling form, I can scale this, and based on the scaled imperfection, I can also apply imperfection. So it's a kind of pre-deformation, and here we display the FE mesh nodes. Okay, so what do we have for methods for stability analysis? So when do I need to consider these imperfections, which we handled on the last slide? Normally only when I do second order analysis. So on the left side, we have one method. This is method A. Here we consider a global and local imperfection, and we calculate the structure according to second order analysis. The way of performing this design check is only the cross-section design. So in order to consider the stability, we only do a kind of cross-section design check with internal forces according to second order analysis. So this is the one extreme. The other extreme is method C. Here we don't need to consider any second order effects. Here we refer to the equivalent member method. This is also the method you learn very often in your study. Yeah. So we calculate the structure according to an geometrical linear analysis, so first order, on an ideal structure, so with ideal internal forces which normally don't appear in the reality. But we have to calculate the equivalent member length, and this is something what we can do for easy structures with a with the help of some tables and some books, or we can also consider this with the help of our add-on structural stability. And the combination of method C and method A is method B. Here we consider these misalignments with the application of global imperfections and calculate the structure according to second order analysis. So when I prove then stability analysis, we do this according to so we do this with the help of the results of the second order analysis. On top of that, we apply imperfections globally. So only these initial sway imperfections. And then we can take the member length as the equivalent member length in order to perform our stability analysis. So, yeah, what do we need to consider else? So the member imperfections are already included in the stability design according to Eurocode 3. And when I want to consider also additional applications of initial bow, you have to determine it for internal forces and moments in sensitive structural systems. So there you have to consider these things. But normally it's not necessary. Only when you have here this sensitive structural system, then you have to consider these things. And here it's a kind of condition for that. And now it becomes very important when I calculate my critical load factors with the add-on structural stability, then I get the results for my buckling length and also the critical load factors. But it's only for the flexural bending. Yeah, the stability failures like torsional buckling and lateral torsional buckling aren't considered. So if I want to take this into account through the eigenvalue analysis using the structural stability add-on, then I have to calculate according to 7 degrees of freedom. And then I can refer to the results because then they are correct. So again, to summarize it, when I calculate a structural stability of a structure, then I have only 6 degrees of freedom, and the result is only valid for the flexural buckling. So now let's come to the stability analysis approach. So I have here global and local imperfections, as well as consideration of all special effects and structure analysis. So I calculate with real internal forces according to the second order analysis. And the other way of approach is determine the ideal internal forces without or only partially considering imperfections. So it's method B and method C from the structural deformation. So all not considered effects must be included in the design method. So now I was talking the whole time about flexural buckling, torsional buckling. How does it look like? So we have different forms of stability failure. So on the left side, we have the flexural buckling. It's stability failure under compression force, buckling around the local axis. So we have a lateral deformation, and this can be considered with 6 degrees of freedom. Now let's come to the torsional buckling. So the torsional buckling appearing on point symmetrical cross-section, such as this cross-section. Here we have a pure rotation around the longitudinal axis of the cross-section under compressive normal force. And a combination of both of these is the lateral torsional buckling or the flexural torsional buckling. So it's a combination of both. I have a lateral deformation and on top of that, a rotation of the cross-section. And the critical load factor here on the left side, this alpha critical, is the ratio between the critical load and the existing or acting design load. Okay. Now let's come to the example. We will model a flat hole frame with this kind of information. I will model it quite fast because we are now quite good in time. And then we do here kind of stability analysis. So let's go here to Rfem 6. I will delete the whole thing. I will create a new example, remain here in the 2D plane. I create, I have to take a look to my notices. Okay, so first of all, I will create a column. It has a section of HEB 300. I click on OK. And the height of this column is 8 meters. And now I create another sections. I go here to the data navigator. I click here on edit, and I want to copy this IPE 550 profile. I have already copied it here and put here 550. And then I want also to copy this section and have here a profile of 180. Okay, good. This was everything. So, and the next part is creating here the upper beam. So create this one section and create here IPE 540. It has a length of, let's take a look, 50 meters. Now I can easily by drag and drop copy it from one side to the other side. And the next part is that I want to connect here an additional frame, an hinged frame. So I choose here the whole beam, model it from there to there, edit here the coordinates to 12 meters because it's shorter, and then create a new column with a section of HEB 180. And double click on that because I said it's a kind of truss. So on both ends we get hinges. I activate the option hinges and create new hinges. I activate here these moment hinges on both ends. I click OK. And now I copy here this one, right click, say mirror it to the other side, create a copy, choose the right plane and also the right mirror point. And this is the middle of this frame. I click OK and we see it here. And now what I have to do is when mirroring something, I have also to check if the section has the right rotation angle. And in this case, I have to change it to 0. I click OK. So I select here all these bottom nodes, assign them here and support, nodal support. And now I want to divide here these members. Right click, members, go here to divide member, intermediate nodes. I choose here 4 because here on these nodes I want to apply nodal forces. And I do this here for the other ones. Perfect. And now I create here my loads. So first of all, I go here to actions in this, to load cases. The first one is the self-weight. I can leave it like that. The second one is snow. I change the action category to snow. And the other one is wind. I change here the action category to wind. And because I have activated here the combination wizard, all these combination of different actions are done automatically. Yeah, you see it here. And also here the load combination, you see this one, how it acts. We have always a kind of leading load action category because there we consider the full partial factor. Okay, so this was everything regarding the load cases and combinations. I click here on self-weight, I say okay. Now let's apply the load. For the load case 1, self-weight, we don't have any loads. Now let's take a closer look to the snow loads. So here I want to consider point loads with 20 kilonewton. I choose here these nodes. I click OK, say apply and next. And for the outer nodes, only 10 kilonewton. And this is a really nice advantage of Rfem 6. I can remain in the same dialog. Just choose different nodes, say OK, and OK again, and we have it like here. So, and now for the wind load, I apply here a member, so a member load for the global X direction. It gets a load magnitude of 2 kilonewton per meter. I choose here the the left column. I say okay, so it's my pressure side. I say apply and next, and for the suction side I have a load magnitude for as 1 kilonewton per meter, and I choose the right column. I say okay. Okay, perfect. And yeah, this was everything regarding the whole load application. Now I want to see if I have to calculate according my first order, so to the geometrical linear order, or to the second order. So in order to do that, I have to activate again my add-on structural stability. I click OK, and what is very nice that I can go here, for example, to the design situation, right click on that, I click edit, and here I can activate the combination wizard, load combination, second order, and now I only want to do the geometrical linear analysis, edit it, and now I want to consider the stability analysis. I click on OK, and now take a look what happens here at the load combination. Each load combination gets here this critical, so the option to calculate the critical load with the add-on structure stability. And now I click here on calculate all, and now let's take a look what happens right here. So first of all, okay, it calculates the load cases, but next to that also the static analysis and then also the load combinations, and this makes it pretty interesting. So in order to see a rough overview about the static analysis, it always is good to take a closer look to the design situation. And here the design situation gives me an information about the stability analysis and the minimum critical load factor. And I see, okay, the minimum critical load factor is 6, so we are under 10. So normally we should consider the effects of second order. And we see also the load combination, which is responsible for this value, and this is the load combination 3. So let's take a closer look to the load combination 3. Okay, this is this load situation, and now I jump here to the stability analysis, and I see here this different mode shape and also this buckling shape. In order to show me the results a little bit nicer, I can go here to deformation, members, and say, okay, section colored. Okay, so nice. So what next? I see here the critical load factor. So the critical load factor says to me, here with a factor of 6, I have to multiply the existing load in order to fail due to stability problems. And I can also see here the results by member. And when I go here to the tab effective lengths, I see here also for the mode 1, the effective length factor of 3. And this is also possible for different members, like member 3. I can also go here, see this one, and so on. And this makes it very interesting because these values, they are necessary for my stability analysis when I want to design it according to the equivalent member method, so method C. Okay, here we have this value, remember it, almost 3, and here also almost 3. So what we do here is that we consider this for the stability analysis for my steel design. So we have 3 different methods for the stability analysis for my steel structures. Now I refer to my method B, so to the last one. And as you can remember, there we don't need to consider any second order effects, but we need to consider the right buckling lengths. Okay, how can we do that? Generally, every member has design properties. Yeah, when double click on one of the member, I see here the design properties. And when I activate the add-on Steel Design, it opens the option for design properties and also additional tabs in order to define several types of design. And there I can say that I want to assign effective lengths, boundary condition, or also shear panels and so on. And now I want to consider this. So for this column, I have here a buckling length or a buckling factor of 3. So I create here a new one. Now this new dialog opens and I can say, okay, how should the whole thing be determined and which effects should be considered. And now we can see here also torsional buckling. For that, it should be considered lateral torsional buckling, and especially the determination of elastic critical moment. So for the lateral torsional buckling should be done by the eigenvalue method. Okay, now how we can assign that? Click here on the tab Nodal Support and refer here to this one. Yeah, but in this case it's like that. So we have here node 1 and node 2, and then let's give here the factor of 3, and this was everything. I click OK. I say yes, and now you see here these kind of supports, but these supports are not globally set. They are only on the member who has these design type configurations or design type boundary conditions. I click on OK. And in order to show you these supports, I go here to the display navigator, go here to types for steel design, and activate here the member effective lengths. Now let's make it a little bit bigger. And now we can see it here. So these are the supports. And this is pretty important to have here these supports. Okay, now let's do this for the other one. In this case, I want to refer to my stability analysis. So I want to take the result calculated with the add-on structure stability in order to take the results for the buckling factors. So again, double click on one of these members, design properties, design types, and go here to create effective length. And now I activate here the option import from stability analysis. And now I can choose here this stability analysis. I refer to my load combination of 3, mode number. Yeah, this is this one. And the member is this one. And now this is the 2.89 for this principal axis. So yeah, because I only consider the effects in plane, not out of the plane, the about the z-axis is not important for me right now. So and now I can also create another effective length where I refer also to the same values. So I I go here again and perform stability analysis. Okay, say load case 3, but in this case for this one, here we have this axis, and now I have now I have to refer it to my member. I say okay, click on OK, but in this case it's the second one, and now we see it here. And for those things, we have now here another where we do effective length here, the third one. Now let's edit it, assign it to this one and also to this one. Okay. And the last one is here, the upper beam. Yeah, the upper beam. And for that, we do the same one. So I double click on one of this one. Oh no, well, let's do this another way. I go here to the effective length, create a new effective length, and say, okay, the nodal supports should be automatically detected by this member. So now you see here, okay, we have here different intermediate nodes, and I don't have to put them manually. They can also be detected automatically just by selecting the correct member. Now I want to have a lateral support, so activate here the fixed in Y direction, the upper flank, and let's do this also for the other ones. Yeah, for this one. And yeah, the principal axis remains like that. And now it becomes very interesting. I can refer it to this member and to this and to this. And although they have different lengths, it doesn't matter. These intermediate nodes are detected automatically. So you see here, okay, it fits. Yeah. I say okay. And now you see here these boundary supports, boundary conditions. And now I can say, okay, let's perform the stability, let's perform the steel design. So I say, okay, steel design, please perform it. And then you will see the stability design, and now it works. Yeah, and this is a huge advantage because in order to consider the stability effects, you have also to add effective lengths or boundary conditions. So, and when I have to add effective lengths, this is for the effective equivalent member method. So now, again, the huge advantage for you is double click on one of this proof, and now you see the longest the longest design check in the whole structural engineering field, because this is the bending and buckling check of steel structures. Yeah, and now you see here different results and values, and you can compare it with your own results. Yeah, pretty nice. Okay, this is one method. This was the equivalent member method. Now let's do another one. So let's do the method B. Therefore, I choose all these. Let's delete them. Yes, I choose all these effective lengths. and they remain, but they are blue. Blue means they are not assigned to anything. So in this case, I create another one. So I double click. No, I don't create another one. I take the first one, and I say to him, okay, I want to consider this one. So a kind of Euler case 2, because the method B said, okay, I have to consider second order analysis results, and also I perform the stability analysis according the normal length of my members. And this is the reason why I do this one. And I refer it to these columns. I say, okay, and this was everything. And now I have to apply imperfections. Let's take me a closer look to my notifications. Okay, perfect. Now we have different possibilities of application of imperfections. So how can we do that? In Rfem 6, the imperfections are already considered into the main program. So create here a new imperfection case, say new imperfection. And now I want to create local imperfections. I say they should act in the global X direction. So this is the name. I say, okay. And now, because of the local imperfection, I get a new field of inserting the local imperfections. So I click here on member imperfection and say new member imperfection. And there I want to consider an initial sway as imperfection type and say, okay, here we have the definition type. I want to consider this according to the Eurocode 3. And the basic value, as I already told you in one of my PowerPoint slides, is here according to Eurocode 3, 1/200. And now I can reduce this factor by giving him the right conditions. So in this case, the structure height. So I choose the member height or the column height of this, and the number of columns in one row is 1, 2, 3, 4. And you see, okay, the initial sway, the value is now 1/350, and I assign it to these columns. I say okay, again on okay. Now I can show me the imperfections. This is one way of application of imperfections. The other way is that we refer also to buckling shape. Yeah, so I delete this again. Now I create a new imperfection case. And now I refer to my buckling mode. And now I have to select a load case. So in order to do that, I have go to, and I want to consider it here for my snow loads. So for this one, this should be my reference for my buckling mode, because here we get normal vertical, full vertical forces. So I go here to edit active load case, and here I calculate the critical load, also again with a structure stability add-on. I say okay, I say yes. And now I go again here to the imperfection, create a new imperfection case, and my imperfection type is now the buckling mode. And here I select the load case, and the load case is in this case load case 2. Buckling mode number 1 is the right one, and the imperfection direction should be in the global X direction with an imperfection magnitude of 0.02. Why this value? This is nothing else than these 1/350 times the height of my structure. Yeah, and this is 8 meters, so 100 per 350. What we have in the local imperfection times the height of my structure is here this imperfection magnitude of 0.02. Now I leave it like that. I say okay. Now I see here this imperfection case, and I can also see the inclination of my structure. So let's show me the results, and we say okay, the FE mesh nodes should be deformed and 20 millimeters. Let's take a closer look to the global deformation, and here we can see okay, here we have a global deformation of 20 millimeters. And now based on that, we refer now our load combinations according to the second order analysis. So what I have to do again is I go here to the design situations, right click, edit, and now I want to consider here the second order analysis without any stability analysis, but consider the imperfection cases. I click OK. Now let's take a closer look to the load combinations. And here we can see these load combinations, which considers the imperfection. And this is the way I want it to have. So I click calculate all. And now we have also considered the stability analysis. So let's go here to the steel design and choose maybe this column here. And here we see, okay, we have a stability design, bending and buckling about the principal axis. And when I took here this upper beam, then we have also the lateral torsional buckling. And when I go here, you see also the eigenmode of this one. Okay, perfect. This is the way of doing stability analysis with Rfem 6, considering imperfections. So to put it in the kind of nutshell, what have you learned today? First of all, how you design steel members as simple cross-section code check. Then you have learned the different analysis methods for different cross-section classes, so plastic and elastic. Then you also got an insight into the whole imperfection topic. So why do we need imperfections, and the different methods for stability analysis when doing a design for steel structures. And then we have performed two different methods. The last one was method B. And the first one is method C, so equivalent member method. And the equivalent member method is pretty important for your study because I did it a lot of time, and now I could show you how you do this also in Rfem 6. Okay, before we end the session, I want to recap the knowledge by giving you two polls. Please answer the one. Okay, most of you have chosen. I close the poll, share the results. And yeah, remember, when you want to consider buckling shapes in order as application of imperfections, then the normal structure, the structure stability add-on in Rfem 6 considers only 6 degrees of freedom. So only flexural buckling is possible. Yeah. If you want to consider the other ones like torsional buckling and the combination of torsional buckling and flexural buckling, so the lateral torsional buckling, then you have to do this with 7 degrees of freedom. And now the last question. Okay, perfect. Let's close this and share the results. So the right answer is, when should I consider second order analysis effects, is when the load critical factor is less than 10. Yeah, so between 1 and 10, when you see, okay, I have here kind of a 7 or 8 as critical load factor, then I have to consider a second order analysis effects. So I have to use these results with second order analysis. Okay, this was everything from my side. Markus, anything from your side?
No, there aren't any unanswered questions on our chat at this moment. I think all is okay.
Okay, thank you, Markus. So I would like to thank you for your attention. I hope you learned something new which will help you for your study, but also for your future work when you are working in an engineering office and you are using our structural analysis programs. With these words, I wish you a nice week, stay healthy, and I hope you will see us next time when doing the online training for concrete structures. Goodbye.